Hello and welcome back dear student in the next module of the topic solution. So in the last lecture we have done our second colligative property, that is elevation in boiling point or boiling point elevation. So in that here we have seen the relation between M2, that means the molar mass of the solute, and that colligative property, and therefore M2 which is equal to 1000 kb W2 divided by delta TB W1. So this is the relation between molar mass of the solute and the colligative property, that is here delta TB. So delta TB which is equal to kb 1000 W2 divided by M2. So this is the relation between delta TB and M, and therefore the molar mass of the solute M2 which is equal to 1000 kb W2 divided by delta TB W1. That means in the elevation in boiling point or in the boiling point elevation, it is calculated the molar mass of the solute. That means the elevation in boiling point, as we see in our last lecture, the elevation in boiling point delta TB from the thermodynamic consideration, it depends on the molality of the solution, and molality which is equal to N2 divided by the mass of the solvent in kilogram, and therefore in that we have to prove that the boiling point elevation or the elevation in boiling point is an colligative property. Boiling point elevation is an colligative property. So here we have done our second colligative property, that is elevation in boiling point. So let us start with the next colligative property, that is the depression in freezing point. Depression in freezing point. So for the depression in freezing point, here first we have to define what is mean by freezing point, and therefore the freezing point of the liquid, because all these properties they shown by the liquid. So all boiling point, vapor pressure, freezing point and osmotic property, all these properties they are the properties of the liquid. So the freezing point of liquid is the temperature. It is the temperature at which the liquid and solid are in equilibrium. When the liquid and solid they are in a equilibrium, and the two phases they have the same vapor pressure. The two phases they are having a same vapor pressure. So the boiling point, so the freezing point of a liquid is defined as the temperature at which here the temperature at which the liquid and the solid are in equilibrium, and the two phases they have the same vapor pressure. So just like the boiling point, here we have considered this graph of the temperature versus vapor pressure. Temperature versus vapor pressure, because the boiling point and the freezing point they are having a direct consequence with the vapor pressure. The boiling point it depends on the vapor pressure, and also the freezing point it also depends on the vapor pressure. So in the graph temperature versus vapor pressure, here in the graph of temperature versus vapor pressure, so in this graph temperature versus vapor pressure, the same graph we have seen in our elevation in boiling point, and in that the delta TB is directly proportional to delta P. That means if we plot a graph of a temperature versus vapor pressure, then in the elevation in boiling point, it is observed that there is an elevation in boiling point of the solvent when a non-volatile, non-electrolyte solute is added to the solvent to form a solution. So the boiling point elevation, they are having a direct consequence with the lowering of vapor pressure. So in the depression in freezing point, if we consider this graph, and from this graph here we have to prove that here delta P is directly proportional to delta TF. What is mean by delta TF? Delta TF is called as a depression in freezing point. Delta TF is called as a depression in freezing point. So from this graph here, there is a depression in freezing point of the solution takes place when a non-volatile, non-electrolyte solute is added to a pure solvent. That means when we add a non-volatile, non-electrolyte solute and form a solution, then there is a depression in a freezing point takes place. That means the freezing point of the solution is lower, is decreased than the freezing point of a pure solvent. That means that depression, that delta T here, it is denoted by letter delta TF. Means in this graph here, if we have considered in this graph here, if we have considered this is the solvent and this is the solution, that is the graph from the elevation in boiling point. The solution, they are having a lower vapor pressure because this is the graph of temperature versus vapor pressure, and if we freeze that liquid solvent and solution, then it is observed that there is a depression in freezing point of the solution. There is a depression in freezing point of the solution. Means the freezing point of the solution is get depressed when we add a non-volatile, non-electrolyte solute to it. So here, therefore, from this graph, the delta P, that means the vapor pressure, they are having a direct consequence with the depression in freezing point denoted by a delta TF. So here we have this graph, and from this graph we can say that, so from this graph here we can say that the freezing point of the solvent is lowered. The freezing point of the solvent is lowered when we add a non-volatile, non-electrolyte solute into it. That means the freezing point of a solution is lower than that of the pure solvent. Therefore, if the freezing point of a pure solvent is denoted by a letter here T not F, F for freezing point, and in that boiling point elevation, B for a boiling point, and the freezing point of a solution is T not, if it is equal to TF, if it is equal to TF, then if the freezing point of the pure solvent is T not F and the freezing point of the solution is TF, then here the depression in freezing point delta TF, which is equal to delta TF, which is equal to T not F minus TF. Depression in freezing point means the freezing point of a solution is get depressed when we add a non-volatile, non-electrolyte solute into it. This is the freezing point of the pure solvent and this is the freezing point of the solution, and the difference is called as the depression in freezing point delta TF. Delta TF. Just like the elevation in boiling point, from the thermodynamic consideration and the experiment, for a very dilute solution, it is observed that this delta TF is directly proportional to M. This delta TF is directly proportional to M. M means the molality of the solution. So, how we can define the molality of the solution? The molality of the solution is defined as the number of moles of solute, present in 1 kilogram mass of the solvent. That means here M, which is equal to N2 divided by W1. 1 for solvent, W for weight, and which is in a unit kilogram. And therefore, if we remove this proportionality sign, then here we have delta TF, which is equal to, here if we remove the proportionality sign, then there is a one constant called as the proportionality constant for a freezing point, depression in freezing point. Therefore, it is called as a Kf into M. Therefore, the delta TF, which is equal to Kf into M here. Kf into M here. And therefore, delta TF, which is equal to Kf into M, where M is the molality of the solution and Kf. So, here the Kf is called as molar depression constant because it is in the expression of depression in freezing point. And therefore, the Kf is called as a molar depression constant, or it is also called as a cryoscopic constant. The Kf is called as a molar depression constant, or it is also called as a cryoscopic constant. It is called as a cryoscopic constant. And what is the value of Kf? And therefore, Kf, which is equal to delta TF divided by M. Therefore, the Kf, which is equal to here delta TF divided by M. And therefore, here if M, which is equal to 1, means if the molality which is equal to 1, molality which is equal to 1 means what? The 1 mole of a solute present in 1 kilogram mass of the solvent, then that solution is called as a molal solution having molality 1. And therefore here Kf, which is equal to delta TF upon M. And if the molality of the solution which is equal to 1, then here Kf, which is equal to here Kf, which is equal to delta TF. And therefore the Kf means the molar depression constant or ebullioscopic constant is defined as depression in freezing point produced for a 1 molar solution. Because here Kf, which is equal to delta TF for M is equal to 1. 1 means a solution having molality 1. And therefore the Kf, which is equal to delta TF, that means here we can define the Kf means the molar depression constant as here the depression in freezing point produced for the 1 molar solution. The depression in freezing point produced for the 1 molar solution. Therefore, here Kf, which is equal to delta TF, called as a cryoscopic constant. It is called as a cryoscopic constant. So, here we have a depression in freezing point delta TF, which is equal to Kf for M, which is equal to 1. Then what is the unit of a Kf? As we know here, Kf, which is equal to delta TF upon M. And means the depression in freezing point and which is having unit Kelvin, and the molality having unit mole per kilogram, mole per kilogram, and therefore the Kf having a unit Kelvin, kilogram per mole. They are having unit Kelvin, kilogram per mole. So the Kf, the unit of Kf and Kb are same. Kb is called as a ebullioscopic constant and Kf is called as a cryoscopic constant. Kf is called as a cryoscopic constant. So just like the elevation in boiling point, from the elevation in boiling point we have to calculate the molar mass of the solute. So from the depression in freezing point also we can calculate the molar mass of the solute. We can calculate the molar mass of the solute. And therefore here we have started with the delta. Here we have a delta Tf which is equal to Kf into m, and as we know m be the molality of the solution, m which is equal to N2 divided by W1 weight of the solvent in kilogram, and therefore N2 which is equal to W2 upon M2, N2 which is equal to W2 upon M2. If we put this value in this equation, then delta Tf which is equal to Kf, N2 means W2 upon M2 divided by W1 in kilogram. But always remember that this W2 is in a gram, M2 which is in a gram, and this W1 which is in a kilogram, and therefore here we have to multiply this equation Kf into M2 into 1000. So the kilogram which is converted into gram, because 1 kilogram which is equal to 1000 gram. 1 kilogram which is equal to 1000 gram, and therefore here delta Tf which is equal to 1000 Kf W2 divided by M2. If we rearrange that, then we have M2 W1 or M2 which is equal to 1000 Kf W2 divided by delta Tf W1. So from the freezing point depression or depression in freezing point, we have to calculate the molar mass of the solute. We have to calculate the molar mass of the solute as M2 which is equal to 1000 Kf W2 divided by delta Tf W1. So from the depression in freezing point, we have to calculate the molar mass of the solute. Here we have calculated the molar mass of the solute as M2 which is equal to 1000 Kf W2 divided by delta Tf W1. So here we have completed our third colligative property as a depression in a freezing point. So next here we have one question, that is, while considering the boiling point elevation and depression in freezing point, a solution concentration is expressed in terms of molality and not in a molarity. Why? This is our question. What is our question? When we have considered the elevation in boiling point and depression in freezing point, then we have used the concentration terms molality. That means here delta Tb V is directly proportional to M, and also delta TF is directly proportional to M. Therefore, we have to use the concentration terms molality instead of a molarity. Why? What is the reason behind that? Because as we know here, molality, which is equal to number of moles of solute present in 1 kilogram mass of the solvent. This is the definition of a molality. And what is mean by molarity? Molarity is the capital M and it is equal to N2. That means the number of moles of solute present in 1 liter or 1 decimeter cube volume of the solution. So the volume of the solution which is taken in decimeter cube or either in a liter. So the molarity depends on the volume. Molarity depends on the volume, and according to the Charles law, which we have studied in our 11th standard topic, states of matter, V is directly proportional to T. V is directly proportional to T. That means the molarity depends on the V and V depends on the T, and therefore the molarity changes with the change in temperature, because the molarity changes with the change in temperature. But in the molality here, the temperature term is not in mole, because it depends on the weight or mass, and mass not depends on the temperature, and therefore here instead of the taking molarity as a concentration term, here we have to take the molality as a concentration term to describe the boiling point elevation and freezing point depression. So this is the reason, because the molarity depends on the volume depends on the temperature, and therefore the molarity changes with the change in temperature. Therefore we cannot use the term molarity, we use the term molality. So this is the reason why we consider the molality instead of a molarity. So dear student, here we have completed the two colligative property. From the last lecture we have completed the boiling point elevation, this colligative property, and in the today's lecture we have completed our third colligative property as a depression in freezing point, that is delta TF, which is equal to KF 1000 W2 upon M2 W1 and M2, which is equal to 1000 KF W2 divided by delta TF W1, with one reason. That is why we use the term molality instead of molarity. So dear student, here we completed, with this lecture we completed the three colligative property. The first one is lowering of vapor pressure, the second one is elevation in boiling point, and the third one is depression in freezing point. But the second and third property, they are having or they are dependent on the first colligative property, that is the lowering of vapor pressure. So we stop here. We will meet in our next lecture. Till then, thank you.